This is 5 Minute Friday with part 1 of how artificial general intelligence is not Nigh. In episode number 565 of the Super Data Science Podcast with Jeremy Harris, Jeremy argued that artificial general intelligence, which is AGI for short, and it's a single algorithm that has the capacity to learn anything a human could. So Jeremy argued that AGI might only be a few years away in that episode. The crux of his argument, which is held by many folks I've talked to off-air in recent months, is that large language models like GPT-3, PaLM, and Lambda exhibit capabilities on tasks beyond what they were expected to be able to by their designers by virtue of them having an order of magnitude more model parameters relative to their respective predecessors. Given that every couple of years recently, the number of parameters in these large natural language models become 10 times greater, proponents of the AGI is Nigh hypothesis, like Jeremy, posit that in the next decade, the number of model parameters in a large language model could reach the number of connections between neurons, between brain cells in a human brain, right? So there's this point approaching in the future where large AI models could have as many model parameters as there are connections between neurons in a human brain, all right? Since modern AI systems, what we can call artificial neural networks, are loosely inspired by the way biological brain cells work, these AGI is Nigh proponents then make the big assumption that once scale on the order of human brain connections is achieved in machines, then an algorithm with human-level intelligence will emerge. As a neuroscientist, my instinct is that this big assumption that model scale is by itself largely sufficient to facilitate AGI is excessively generous. Human brains, or indeed the brains of even much cognitively simpler organisms like birds, reptiles, and other mammals, these contain a vast amount of anatomical complexity that enables them to exhibit their broad and efficient learning capabilities. To name a few examples from the dozens of examples that I could, we have specialized brain structures like the amygdala, which plays a leading role in processing emotions. We've got the hippocampus that plays a specialized role in memory formation. And we've got specialized areas like the fusiform face area that are critical to recognizing the faces of other humans specifically. We don't understand any of these areas well enough to model them effectively with a machine, and there are probably anatomical regions of the human brain that play a critical role in our intellectual capacities that we haven't even discovered yet. Modern AI systems make heavy use of the transformer architecture and then replicate that transformer architecture over and over to remarkable effect, no question. But this is meager complexity relative to the dozens of varieties of interacting anatomical components in the human brain. In addition to artificial neural networks being relatively uniform and vastly simplistic in their gross anatomical layout relative to biological brains are also vastly more complex at a small scale, that's at the cellular level. Firstly, artificial neurons are computationally simpler than the biological ones that they mimic. And secondly, biological brains have cells other than just neurons that play a role in building and retaining memories and behaviors. Despite their role in intelligence, these support cells, other than neurons, with names like glial cells and oligodendrocytes, these support cells have not been modeled in AI systems in any meaningful, large-scale way. Finally, on top of AI systems not having anywhere near the gross anatomical complexity nor the cell-level complexity of biological nervous systems, biological brains also carry out massively parallel processing. At any given point in time, your brain has countless brain cells processing information signals in parallel in a way that computer systems are nowhere near replicating. While it might be only a decade or so until there is an algorithm with as many model parameters as there are connections between neurons in a human brain, it would take a vastly different computing approach than the one that prevails today, perhaps one day something like quantum computing, to have anything like the massive parallel processing of a biological brain. And this kind of vast scale in quantum computing is not yet visible on the technological horizon. So in summary, Due to gross anatomical, fine-grained cellular, and parallel processing differences between biological nervous systems and AI, the model scale alone, AGI is Nigh hypothesis doesn't hold much water from my neuroscience perspective. For 5 Minute Friday next week, I'll review the leading AI expert Yann LeCun's learning approach-based perspective as to why the model scale AGI is Nigh hypothesis doesn't seem credible to him either. Until then, keep on rocking it out there, folks, and I'm looking forward to enjoying another round of the Super Data Science Podcast with you very soon.